we did a digital oscilloscope, and these are the requirements. We're using the microglaze to design a digital oscilloscope, and we're connecting two boards together, the Nexus 1 and the Nexus 2 board. The Nexus 1 board is basically collecting data from an external source. Basically, it's the analog voltage input, and then process the data. For the sampling voltage, we use the 8D converter. And the Nexus 2 board, we basically just display the waveform. So, display the waveform on the VGA monitor. And the oscilloscope is operating in a run-stop fashion. So basically, it's user control. So when the user presses the button, so it runs, and then it releases. If the user releases the button, it stops. So here are the block diagrams. This one is the Nexus 1 board block diagram. So basically, we have the PMOD A to D. It collects the voltage analog input, and then the SPI receives the sample waveform, the sample data. And then we have the timer counter generates an interrupt. And then also on the, we have the LCD, LED, and the buttons, the GPIO. And then for sending the data to another board, the Nexus 2 board, we are using the UART. And on Nexus 1, we enable the transmit register. And on Nexus 2, we enable the receive register. So it sends data, and the Nexus 2 board collects the data, and then it sends out to the VGA port and then display on the VGA monitor. And we kind of switch to the UART is because we didn't use SPI because the slave configuration in Xilinx basically is broken down. So if we do the master, the Nexus 1 board be the master, and then the Nexus 2 board be the slave, basically didn't work. So we switched to UART, and also we don't have to go through all the configuration steps for the UART because we have to go through the configuration steps from SPI. So basically it's simpler and easy to use the UART.
In the Nexus part 1 is for data sampling, and we have bandit control, which allow the user to fill information such as frequency, time division, voltage division, and other informations. And it also allows us to increase or decrease the time division, voltage division, and move the waveform up and down. And also it allows us to control when to start getting data. And for getting data part, we actually just accept any source such as battery and function generator for the input data, and it works for any regular waveforms such as sine waveform, square waveform, and other waveforms. It will gather 5 data points, and it will automatically stop, and then it will take those data to to calculate frequency, amplitude, period, and other information that we need.
So once the data is
Oh, and then the way we send the data is using a big array, holding the data and the info that we gathered through the processing data, such as the frequency and all that. And after we send the data, we determined what order we would send it, such as data, then frequency, then period. We determined that between the two boards. And after all that, we refreshed the LCD screen to display the information we need.
So on the data display app, we sort of have a very simplistic flow chart that we go through. So we start, when the board starts up, it initializes the VGA connector. And we'll go into that in a minute. And then when we receive an interrupt for the UART, meaning we've received data from the other board, we read in the 16 bits of data from the receive FIFO, classify the data as whether it's a waveform or information such as the frequency or amplitude, format that data as needed for our VGA display, and then output it to block RAM. So the actual VGA display was actually written in VHDL because Microblaze does not have the performance needed to drive a 40 megahertz pixel clock for the VGA display. So we wrote everything in VHDL at a very low level and imported it as a single IP core within Simon's Platform Studio. So we have one module that essentially just generates the horizontal and vertical sync signals for the monitor at a resolution of 800 by 600 pixels and a refresh rate of 60 hertz. Then we have a character generation engine that's actually a three-stage pipeline. So we will pull out which characters should be drawn from the information gram. So those are the numbers you'll see on the screen for the frequency, period, and so on. And then a character gram is actually a mapping of all the characters we can display on the screen. And so that data is read through here and then piped over to the pixel generator, which determines what colors to be shown on the screen and outputted to the VGA display.
Okay, and we tested the board by separating into two groups. One group would do the data gathering, the other group would do the VGA display, and we were able to test the data gathering just using either a battery or a function generator, even from our project 4. And we would test the VGA just by putting kind of fake data into our code and outputting it to the VGA. And when we were connecting it together, we tried using the SPI at first, but we ran into problems there. So we switched to the UART, and it was much simpler to implement, and we didn't need the speed from the SPI, so it worked. And the transmission, we adjusted the format, so we determined what to send first, what to send next, and we also included a first send that told us that we're starting to send data to the other board. And our code ended up for the Nexus 1, used almost all the slices available and about 800 lines of code. And for the Nexus 2, we used about 30% of the slices and about 300 or 400 lines of code in C and about 700 lines of VHDL.
So we have a demo set up over at our lab bench.
So you have the character generator?
Yeah, character generator, the pixel generator, and the VGA signal generator. The way we actually did the characters was we created an Excel spreadsheet that essentially gave us the 10 by 16 pixels, and we just filled in zeros or ones where we wanted the characters to show up. And those actually got saved into a text file that you import into the Xilinx tools that has a memory editor. It generates what's called a coefficients file, and the coefficients file gets loaded into block RAM.
Then you had to go scan.
Correct.
So you translate the pixels into the scan.
Yes. Yeah.
So you did all that.
Yeah. All in VHDL. So if everyone would like to go over to bench 13, we have a demo. I think it's just
Okay, so right now we have about 60 hertz-ish. So every time we want to read, we just press this button. And we can change the